Time stops for no one. But what if we could zip back to the past or zoom ahead to the future? Imagine hopping into a special machine, pressing a button, and suddenly finding yourself in a different time. Witnessing the building of the pyramids, conversing with historical figures, or seeing dinosaurs roam the earth. But is time travel merely a figment of our imagination, or does it hold the potential to become a reality? Let's find out. All the concepts related to time travel are pretty complex, but I will try my best to keep it as simple as possible. Time travel, as the name suggests, refers to the hypothetical ability to move backward or forward in time, allowing individuals to experience events that have already occurred or are yet to come. While the idea of time travel has been popularized by works of fiction such as H. G. Wells' 1895 novel The Time Machine and films like Back to the Future, its scientific feasibility remains a subject of intense debate and speculation. At the heart of our understanding of time and space lies Einstein's theory of relativity. According to this revolutionary framework, time is not an absolute immutable entity, but rather a dimension intricately linked with space in what is known as spacetime. One part of Einstein's theory, called the theory of special relativity, says that time doesn't always tick the same way for everyone. It can speed up or slow down depending on how fast you're moving compared to someone else. Another part, called the theory of general relativity, says that gravity, the force that pulls things together, like making apples fall from trees, can also mess with time. To explain the concept better, imagine that the universe is a big trampoline. The trampoline is like one big fabric made up of space and time woven together called space-time. Now when nothing is on the trampoline, it's flat, right? If you put a small marble, it would cause a little bit of warping on the trampoline because of its weight. But then if you put something heavy on the trampoline, like a bowling ball, what happens? The trampoline bends and warps around the bowling ball. That's what happens in space-time when there's a big object like a planet or a star in it. It bends and warps space-time around it. The amount of warping depends on the mass of the object. Heavier the object, more the gravitational force, more the warping. In space-time, this bending and warping affects how time moves too. Near a big object like a planet or a star, time can actually slow down compared to somewhere farther away. It's like time itself is being stretched or squished by the warping of space-time. Now let's say you're an astronaut floating near the event horizon of a black hole, where gravity is extremely strong. You have a friend who remains at a safe distance away from the black hole. Both of you have synchronized wristwatches. As you hover near the black hole, you notice something strange. Your friend's watch appears to tick faster than yours. Even though both watches were initially synchronized, your friend's watch now seems to be running ahead of yours. This discrepancy occurs because of a phenomenon known as time dilation. In the strong gravitational field near the black hole, space-time is severely warped, causing time to pass more slowly relative to an observer farther away from the black hole. From the friend's perspective, time is passing normally, but from your perspective near the black hole, time appears to be moving more slowly. Now let's consider a more familiar scenario, standing on the surface of the Earth. While Earth's gravitational field is much weaker compared to that of a black hole, it still has an effect on time. Imagine you and your friend each have a wristwatch, and you decide to conduct an experiment. You climb on the top of a tall mountain, while your friend remains at sea level. After some time has passed, you reunite and compare your watches. Surprisingly, you find that your watch, which was at a higher altitude, is ticking slightly faster than your friend's watch at sea level. The difference in the rate at which time passes is also due to gravitational time dilation, though it's much smaller compared to the effect near a black hole. In this case, the gravitational field is weaker at higher altitudes, causing time to pass slightly faster relative to someone at a lower altitude. These examples illustrate how gravity affects time through the phenomena of time dilation. In the regions of strong gravitational fields such as near black holes, time appears to pass more slowly, while in weaker gravitational fields, time passes more quickly. This effect is a consequence of Einstein's theory of general relativity and has been confirmed through various experiments and observations. Another theory is that of wormholes, which are hypothetical tunnels in space-time that connect distant points in the universe. Wormholes have captured the imagination of physicists as potential gateways for time travel. Let's understand this with the help of a simple example. Imagine you're on one side of a big piece of paper and your friend is on the other side. You want to get to your friend, but walking around the paper would take a really long time. Now what if you could fold the paper so that the two sides touch each other? That's like what a wormhole does in space-time. It creates a shortcut between two distant points. So instead of walking all the way around the paper, you could just hop through the wormhole and pop out on the other side, right next to your friend. That's the basic idea behind how a wormhole works. Now let's apply this idea to time travel. Imagine if you could create a wormhole not just between two distant places, but also between two different times. See the past and the future. If you could step through this time traveling wormhole, you might find yourself suddenly transported to a different time period. While the existence of traversable wormholes remains purely speculative, the mathematical viability has sparked considerable interest among researchers. The realm of quantum mechanics offers another venue for exploring the possibility of time travel. Quantum mechanics is a branch of science that deals with really tiny things, like atoms and particles. In this world, things don't always behave the way we expect them to in our everyday world. Instead, they follow some strange rules. One of these rules is called superposition. It means that things can be at more than one place or state at the same time. Imagine if you could be both in your room and outside playing at the same time. That's kind of like superposition. Another rule is called entanglement. This happens when two particles become connected in a special way, so that whatever you do to one particle instantly affects the other, no matter how far apart they are. It's like having a pair of magical socks. If you lose one, the other one disappears too. Now, how do you relate this to time travel? Well, some scientists think that by using these strange rules of quantum mechanics, we might be able to do some pretty wild things, like traveling through time. Imagine if we could use superposition and entanglement to bend and twist space and time itself, like folding a piece of paper. That might create shortcuts or tunnels that could take us to different times. But here's the thing. While it's a fascinating idea, we are still far from knowing if it's possible or how we could do it. The prospect of time travel raises a host of paradoxes and conundrums that challenge our understanding of causality and the nature of reality. The grandfather paradox is a famous thought experiment in the realm of time travel. It goes like this. Imagine you build a time machine and travel back in time to visit your grandfather before he had any children. While you're there, you accidentally prevent your grandparents from meeting or having children. As a result, your parents and consequently you are never born. Similarly, the butterfly effect, popularized by chaos theory, suggests that even minor alterations in the past could have profound and unpredictable consequences on the future. While the theoretical groundwork for time travel exists within the framework of modern physics, the practical challenges of realizing this concept are formidable. The energy requirements for creating and sustaining wormholes, the engineering hurdles of building a time machine capable of withstanding the rigors of time travel, and the ethical implications of altering the course of history are just a few of the obstacles that must be overcome. Beyond the scientific and technological challenges, time travel raises profound ethical and philosophical questions that extend to the very nature of existence and free will. If time travel were possible, would the past be fixed and immutable? Or could interventions in the past lead to branching timelines and alternate realities? What responsibilities would time travelers have to the inhabitants of the past, present, and future? These questions highlight the need for careful consideration of the implications of time travel beyond the realm of science. Whether time travel will ever become a reality or remain confined to the realms of fiction remains one of the greatest mysteries of cosmos, inviting us to ponder upon the nature of time, space, and our place in the universe. That brings us to the end of the video. Alive and Curious is a new channel and would love to have your support. So if you like what I say and do, please like, share and subscribe to the channel. Thank you. See you in the next one.